don't just copy, I analyze tight, spot what's wrong, make it right, dig through errors, call them out, level up, no room for doubt. Today, we're diving into a bold new way to train language models, critique fine-tuning, or CFT. Instead of simple imitation, CFT teaches models to critique mistakes, spot flaws, and refine responses, just like a good reviewer does. It outperforms models trained on over 2 million examples using just 50K data. Let's get started.
Supervised fine-tuning, or SFT, is the go-to method for training language models today. The process is straightforward. Take a bunch of high-quality responses, have the model mimic them, and refine it using human feedback. But here's the twist. This paper asks, what if instead of just imitating correct answers, we train models to critique bad ones? Enter critique fine-tuning. We will call it CFT from now on. The authors built a dataset where each example includes a question, a noisy response, and a critique of that response. The model learns not just to answer but to analyze and refine its reasoning. And the results? A solid 1 to 10% boost in performance across benchmarks like MAth and Olympiad Bench. Take a look at Figure 1 here. On the left, you'll see how CFT outperforms standard SFT across different models on the M8 dataset. On the right, it's the same story for Olympiad Bench. The standout? QN 2.5 Math, where CFT hits the highest accuracy. But it's not just about numbers. The qualitative differences are striking. For example, given a financial analysis question, SFT gives a straightforward but shallow response. CFT, on the other hand, critiques the reasoning, checks for reliability, and delivers a stronger argument. The takeaway? Teaching models to critique might be way more powerful than just teaching them to imitate. Now let's dig a bit deeper. Most large language models today rely on SFT. They're trained to imitate high-quality responses from human-annotated datasets. It works, but there's a catch. Imitation alone doesn't guarantee deep understanding. The model might just be copying patterns instead of thinking critically. That's where CFT comes in. Instead of just learning to repeat good answers, models are trained to critique bad ones. They analyze responses, identify weaknesses, suggest improvements, and even verify correctness. It's inspired by how humans learn through feedback, not just memorization. And the experiments back this up. Models fine-tuned with CFT outperform standard SFT models by 4 to 10 points on reasoning-heavy benchmarks like MAth and AIME24. Even on more complex datasets like MetaMath and NumanaMath, the results hold. The researchers also ran ablation studies to test CFT's limits. They checked if dataset quality mattered. Turns out, WebInstruct had a slight edge due to its variety of topics. They also tested noisy responses and different critique models. Even weaker critique models like GPT-4o Mini still improved performance over traditional SFT. But there are limitations. The critiques in the dataset were all generated by GPT-4o, and about 20% contained errors. Better critiques could mean even better results. Another challenge? Models fine-tuned with CFT can't yet critique themselves. They still need explicit critiques in their training data. Future work might explore making models more self-reflective. Before a model can learn to critique, it needs good training data. So how was the dataset built, and how does it compare to existing ones? The main dataset here is WebInstruct. Unlike datasets focused solely on math competitions, WebInstruct covers a broad range of topics: math, physics, business, humanities, you name it. The catch? The responses can be noisy because they come from large models like QN72B and Mixtral without much verification. To fix this, the authors created several refined versions. WebInstruct-SFT just samples responses as they are, but it has over a 50% error rate. WebInstruct Verified uses GPT-4o to filter out bad responses, keeping only the best ones. WebInstruct-CFT, the star of the show. Here, responses are critiqued by GPT-4o to provide feedback. This is where models learn to critique answers instead of just copying them. Check out Table 1. It shows how CFT datasets compare to standard fine-tuning datasets. While typical SFT datasets have millions of samples, CFT datasets are much smaller, just 50K samples, or even 4K for a compact version designed for smaller models. Now, how is the model trained? The key idea is simple. The model takes a response, and learns to predict a critique for it. The training loss function maximizes the likelihood of generating a useful critique. So the model isn't just improving its ability to answer questions, it's learning how to evaluate and refine responses. This structured approach lets CFT models perform well with far less data than traditional fine-tuned models. So does CFT actually work better than SFT? The numbers say yes, big time. Start with Table 2. It compares the performance of different models on multiple math benchmarks. The takeaway? CFT consistently outperforms SFT. On QN 2.5 Math 7b, its best-performing version hits 57.1% accuracy, beating the strongest SFT baseline by nearly 7 percentage points. On QN 2.5-7b, the gains are even bigger. CFT beats the best SFT model by 10.4 percentage points. Now look at Figure 2. It tracks training progress on Imitate and Minerva math benchmarks. The key finding? CFT converges much faster than SFT. By around step 30, it already surpasses the other models and maintains its lead. On MathM, it hits 80% accuracy, compared to 70% for SFTG and 60% for SFTV. The same trend holds for Minerva Math, where CFT stays 40% higher than SFT models throughout. What does this mean? CFT doesn't just improve accuracy. It also makes models more data efficient, learning faster and reaching better performance with the same training budget. Now, how does CFT stack up against other specialized models? Let's break it down. Start with Table 3. It compares performance across multiple 7B scale models. The standout? QN 2.5 Math 7b CFT, which achieves 48.1% average accuracy using just 50K training samples. That's better than much larger models like Llama 3 to 70B Instruct, 40.4%, and NUMINAMATH 72B COT, 39.1%. CFT is incredibly data efficient. Now, check out Table 4. It compares 32B scale models, specifically QN 2.5 to 32B CFT, versus Sky-T1 to 32B Preview. Here's the kicker. QN 2.5 to 32B CFT only needed 4K training samples to achieve top-tier performance. Sky-T1 to 32B needed 17K samples to reach a similar level. That's a 4x boost in data efficiency. The bottom line? Surface. CFT not only improves accuracy, but also slashes training data requirements. It's a game changer for making powerful models with fewer resources. Now let's talk about reinforcement learning, or RL. It's been widely used to boost reasoning in large language models. But how does CFT compare? Table 5 shows that CFT competes directly with RL-based methods like simple RL, while being far more efficient. Training a model using simple RL takes 1152 GPU hours, while CFT only needs 8 GPU hours. Yet, it still achieves comparable or better accuracy. On some benchmarks, like AMC23, CFT even outperforms RL-based models. Next, dataset quality. Table 6 shows that WebInstruct originally performed the worst with SFT, at just 35.1% accuracy. But with CFT, WebInstruct outperforms both MetaMath QA and Numinamath, reaching 57.1% accuracy. This suggests CFT helps models learn from noisy or imperfect data. Then there's self-generated versus human-created responses. Table 7 shows that self-generated solutions reach 55.1% accuracy, while original solutions do slightly better at 57.1%. High-quality human-created solutions still provide an edge. Finally, Table 8 looks at the role of different critique models. Using a stronger critique model like GPT-4o1120 boosts performance to 57.1%, while weaker models only reach 52.0%. Better critiques lead to better fine-tuned models. In short, CFT is a highly efficient, scalable, and effective alternative to RL-based training, and it even helps models learn from imperfect data. Now let's talk about limitations. Two key challenges stand out: noisy critique data and self-critique mechanisms. First, critique quality. Even with the best-performing dataset, critiques from GPT-4o1120, about 20% of critiques contained errors. Some misidentified correct answers as wrong, while others missed logical mistakes. The takeaway? CFT still works well, but better critiques could make it even stronger. Future work might use human-verified critiques or combine critiques from multiple expert models. Next, self-critique. Table 9 compares different inference methods. The best performing approach? Direct inference at temperature 0.0, where the model simply generates an answer without self-critique. It reaches 80.2% accuracy on math and 42.3% on Minerva math. Self-critique methods, on the other hand, struggle. In the single-pass approach, accuracy drops as temperature increases, from 77.2% to 73.5% on math. The two-stage method, where the model critiques its own answer, does slightly better but still underperforms direct inference. The problem? The model has trouble evaluating its own outputs consistently. Sometimes it flags correct answers as wrong, and other times it misses real mistakes. Higher temperatures also introduce instability. In short, self-critique doesn't work as well as direct inference, so the authors stick with the simpler, more reliable approach for their final CFT implementation. Before we wrap up, let's touch on prior research. This paper builds on three key areas: instruction tuning, mathematical fine-tuning, and critique learning. First, instruction tuning trains models to follow human-like instructions. This can be done using human-annotated datasets like FLAN and SuperNI, or by having models generate their own training data, as in Self-Instruct or Wizard LM. While this improves alignment with human expectations, it doesn't necessarily make models better at reasoning. This leads to mathematical instruction tuning, where models are trained on math-heavy datasets like MAMoth2 and OpenMathInstruct. These help improve reasoning, but at some point, adding more data yields diminishing returns. That's where CFT comes in. It offers a smarter way to train. Next is critique learning. There's a concept called self-correction, where models try to fix their own mistakes. It sounds promising, but research shows it doesn't work well in practice. Unlike self-correction, CFT trains models to critique other responses, leading to stronger reasoning abilities. Finally, the conclusion. The key takeaway? CFT rethinks how we train models. Instead of just mimicking correct answers, it makes models think more deeply by analyzing flawed responses. The experiments show that CFT consistently outperforms traditional SFT by 4 to 10% on mathematical reasoning tasks, even with just 1 to 10% of the training data. Even more impressive, with only 8 hours of training on H100 GPUs, CFT models achieve performance comparable to RL-based models like DeepSeek RL, which require 140x more compute. Beyond math, CFT extends to other domains like STEM and theorem solving. It challenges the idea that SFT or RL are necessary for instruction following. The results suggest new directions for improving LLMs, not just in reasoning tasks, but potentially in multimodal learning, broader applications, and theoretical advancements. Thanks for joining us today. Happy learning and stretching together.